Hi everyone, welcome to Calc Lesson number 68. Today we are going to be looking at section 5.5, so we are going to be differentiating and integrating with bases other than e. So a little bit different than what we've been doing over the past couple of lessons. So we're going to start by talking about differentiation with bases other than e, so taking our derivative. So we have two really important rules right here. The first is if we are taking the derivative d dx of a to the u power. Now something important to recognize is that this u is actually a function of x. So we're looking at now having variables as our exponents. So a to the u is equal to the natural log of a times a to the u du dx. And then the derivative d dx of log base a of u, again u is a function of x, would be equal to 1 over the natural log of a times u, again times du dx. So make sure you have these somewhere or take a picture so you can use these throughout the rest of today's lesson and then on tonight's homework. So for our first example, we're going to start off basic. We're going to find the derivative of our function y equals 2 to the x. Notice how x is our exponent. So we used to handle derivatives when we had a number as an exponent, and we would use our power rule. We would move it down to the front and take it to the 1 less power. However, when we have an x or a variable as our numerator, or as our exponent, we have to do a little bit different. So this is where we're going to bring in this rule from our previous slide. The derivative of a to the u is the natural log of a times a to the u du dx. So in this case, our a would be 2 and our u would actually equal x. So I'm going to take a little note here that u would be x, which makes du dx just equal to 1. So finding our derivative dy dx, following our pattern, this would be equal to the natural log of a, so that's going to be the natural log of 2 times a to the u, so times 2 to the x, times du dx, which is going to be equal to 1. So we can write our derivative dy dx just as the natural log of 2 times 2 to the x. And remember, the natural log of 2 is just a number, so we can leave it in front there. No need to simplify or to find a decimal equivalent. You can just leave it as the natural log of 2. Just notice you have these parentheses to separate what is in the natural log and what is being multiplied separately. Our second example is actually very similar. So we just looked at 2 to the x. Now let's look at our function y equals 2 to the 3x. We're going to follow that same pattern. This derivative of a to the u is equal to the natural log of a times a to the u du dx. You guys know by now I like to identify my u, so I'm going to choose my u is my whole entire exponent, 3x, which makes du dx just equal to 3. Following my pattern or my rule here, my derivative dy dx is equal to the natural log of a, so a is still going to be this base of 2, natural log of 2, times a to the u, so 2 to the 3x, and then times the derivative, which would be times 3. Now we have to be careful when we simplify in what we actually can combine. So 2 to the 3x is the only term that has that exponent of 3x and the only term with a base of 2. So we can't combine that with anything. We have the natural log of 2, that's just a constant, and 3, that's just a constant. So we can actually pull both of those to the front. So we can write our derivative dy dx as 3 times the natural log of 2 times 2 to the 3x. So again, just take note of which values you are able to combine and which you are not. And again, 3 natural log of 2 is just a constant, but we can leave it as that exact value. No need to find your decimal approximate. Okay, now that we saw 2 introductory problems, let's look at a more exciting. So here we're going to take the derivative of y equals 3 to the 2x over x. So hopefully you recognize that we have a function of x divided by a function of x. So ultimately what we're going to have to use here is a quotient rule. So a reminder of the quotient rule, if you have a function f over a function g, you take the derivative by taking g times the derivative of f minus f times the derivative of g all over g squared. So I'm going to start by writing out the quotient rule, and I'm going to write it with my d dx of each piece. So let's write our derivative, y prime, would be equal to, so our function g is going to be our f function, is going to be our 3 to the 2x, and our g would be our x. So here we have g times the derivative of f, and I'm going to write this as d dx of 3 to the 2x minus f, which is 3 to the 2x, times the derivative of g, and just for consistency, let's write this in the right color as d dx of x, and that is all going to be over our denominator, or g, which is x squared. So now we've taken care of the quotient rule, so let's go ahead and do each of those derivatives. So let's start by finding the derivative of 3 to the 2x, and we're going to do that using our new rule. So here our a is equal to 3 and our u is equal to 2x. That makes du dx just equal to 2. So following the formula here, this would be the natural log of a, so the natural log of 3 times a to the u, so times 3 to the 2x, times du dx, which would be equal to 2. So we can say that this derivative is 2 ln of 3 times 3 to the 2x. And then the derivative of x, hopefully we know the derivative of x is just going to be equal to 1. So we can go ahead and fill this in. So y prime is equal to x times, filling in our derivative, 2 natural log of 3 times 3 to the 2x minus 3 to the 2x times 1 all over x squared. And then our final step, just to simplify this, is going to be to recognize that we have a 3 to the 2x in both terms. So let's factor that out to the front. So we have y prime equals 3 to the 2x times 2 natural log of 3x minus 1, and that's all over x squared. So take a moment, look back through. Hopefully you're able to follow the quotient rule, finding each derivative, the yellow and the blue, and then simplifying by pulling out that GCF of 3 to the 2x. Okay, our next example looks a little bit different. Here we want to take the derivative of y equals log base 10 of cosine of x. So this time we actually have to use that second new rule. The derivative of log base a of u is equal to 1 over the natural log of a times u times du dx. So the first thing I want to do is identify my a as 10 and my u as cosine of x. Now I want to pick out the rest of my pieces. So if u is equal to cosine of x, then du dx is just going to be the derivative of cosine, which would be negative sine of x. Now I can follow my formula. So the derivative y prime is going to be equal to 1 over the natural log of a is going to be the natural log of 10 times u, so times cosine of x, and then that whole thing multiplied by the derivative of u, so du dx, which would be times negative sine of x. Simplifying, this would be y prime equals negative sine of x over the natural log of 10 times cosine of x. And hopefully you guys remember your trig identities and you recognize that sine over cosine is just equal to tangent. So we can write our derivative y prime as negative tangent of x over the natural log of 10. So just a little bit different in that there's a different formula for us to follow, but once you identify your a, your u, and your du dx, you can just fill in and then simplify as necessary. Okay, in our last differentiation example, we want to find the derivative of the function y equals log base 3 of the square root of x over x plus 5. Because we have a base of 3, we know we're going to be needing to use our new formula from today. However, we have such a complex piece to start that we want to start by using the properties of logarithms to expand this out. So let's start by rewriting this. as y equals, and we can break our division using subtraction. So log base 3 of the square root of x minus log base 3 of x plus 5. And I'm actually going to change my square root of x to be x to the, 1/2 power, because I know I can pull my 1/2 in front. So this is really y equals 1/2 log base 3 of x minus log base 3 of x plus 5. So starting by rewriting this out, now I can go ahead and use my rule for both pieces. So when we take our derivative, dy dx, we can keep our 1/2 in front. Now when we go to take the derivative of log base 3 of x, that makes our a equal to 3, our u equal to x, and our du dx equal to 1. So this derivative would be 1 over the natural log of a, or the natural log of 3, times u would be times x, and then that whole thing multiplied by 1. Then we can subtract our derivative of log base 3 of x plus 5. Our a is still equal to 3. This time our u is equal to x plus 5, and du dx is still equal to 1. So our derivative here would be 1 over the natural log of 3 times u, which is x plus 5, and then again times 1. So take a second and make sure you can at least fill in all of these pieces. And then from here, I'm just going to do one quick simplifying step. We're not going to find a common denominator, but let's just clean this up a little bit. Our derivative dy dx would be equal to 1 over, combining my constants here, of 2 natural log of 3 times x minus 1 over, and we can leave this as the natural log of 3 times x plus 5. So a little messy, but as long as you remember to use your properties in the beginning, then you can simply use your rule, and it's not too crazy. So before we move into integration, pause, ask your teacher if you have any questions on derivatives of logarithmic functions with bases other than e. So now that we've looked at differentiation with bases other than e, let's take a look at integration with bases other than e. So you have your definition a to the x. So again, we're going to be looking at variables as our exponents. The antiderivative would be 1 over the natural log of a times a to the x. And then because we are looking at indefinite integration, we are going to need that plus c. So go ahead, again, snap a picture if you need this, write it down so that you can use it for the next couple of examples and on tonight's homework. So let's start again with our most basic example. Here we want to integrate 2 to the x dx using our new definition. The integral of a to the x dx is 1 over the natural log of a times a to the x. All we have to do is identify that in this case our a value is equal to 2. And we can go ahead and follow our formula. So the integral of 2x dx is equal to 1 over the natural log of our a value, which would be 2, times a to the x, so times 2 to the x, and then of course we just need a plus c because this is our indefinite integral. So your first and most basic example of integrating with bases other than e. All right, our next example is very similar. We want to integrate 8 to the negative x dx. Unfortunately, it doesn't follow the pattern exactly because our exponent is not just x. There's more to it, in this case a negative. So in order to complete this problem, we need to use u substitution. So let's let our u be equal to this exponent. So if we choose u equals negative x, then du would equal negative 1 dx, which makes dx just equal to negative du. Remember, with u substitution, you then want to go ahead and replace everything you can. So we really want to be integrating 8 to the u times negative du. And because that negative is just really a negative 1 constant, we can pull it out to the front. So this is the negative antiderivative of 8 to the u du. Now we can follow our pattern where here our a value is equal to 8. So this is going to be the negative 1 over the natural log of our a, which is 8, times 8 to the u, and then of course a plus c. And then as always, our final step is going to be to go ahead and replace. So we could write this as negative 1 over the natural log of 8 times 8 to the negative x plus c. So same type of example as example 6. However, because we have more than x, we have to use our u substitution in order to complete this problem. Okay, just a couple more. In example 8, we want to find the indefinite integral of x to the 4th plus 5 to the x dx. Hopefully you recognize that in order to integrate x to the 4th, that would be a power rule, which we have been doing for a long time now. And then in order to integrate 5 to the x, that's where we would have to use our new definition of the integral of a to the x dx. So here we really have to do two separate things. I like to separate these so that my brain can remember to do each piece. But again, it is up to you if you can do that in your head. When I integrate x to the 4th, that's your basic power rule, we're going to take our x to the 1 higher power, which would be 5, and divide by 5. Then when we go to integrate our 5 to the x, following our pattern, that means a is equal to 5. So this derivative would be this antiderivative would be 1 over the natural log of 5 times 5 to the x, and because this is an indefinite integral, this would be plus c. And we can actually leave our answer like this. So just keeping in mind that you still have all of the other rules we've gone over, and when you can separate your integration by doing each piece. Okay, our last example, and this really is going to be the most complicated we're going to look at, example 9, we want to integrate the quantity x plus 4 times 6 raised to the quantity x plus 4 squared. So remember, when you're taking the derivative, you have a product rule, a quotient rule, all of those different rules. When you're integrating, you basically just have u substitution. So even though we have two things being multiplied, the only way we can really handle it is by using u substitution. So our best bet here, because of the definition that we know, is we can only handle an exponent if it is just x or just u. So we need to replace our entire exponent with a single variable. So that's a big hint that let's try using that as our u. So if we use u as our whole quantity, x plus 4 squared, and again we decided that because we need our exponent to be a single variable, using u substitution we need to find du. In order to take this derivative, we need to use the chain rule. So we would bring our 2 down, leave our inside the same, and take it to the 1 less power, and then multiply by the derivative of the inside would just be 1 dx. So we can let's simplify this. We have du equals 2 times x plus 4 dx, which means dx is equal to du over 2 times x plus 4. So let's start replacing and see what happens. Here we have our integral of x plus 4 times, let's replace this with 6 to the u times du over 2 times x plus 4. And it seems like this is working out because our x plus 4 quantity ends up canceling out. We do still have this 2 in our denominator, but hopefully by now you recognize that that is just a 1/2 that can come out to the front. So we really have 1/2 the integral of 6 to the u du, and now we can integrate this using this rule. So integrating we get, keeping our 1/2 on the outside, our a value is going to be 6, so this would be 1 over the natural log of 6 times 6 to the u, and then replacing our u back with what we originally subbed it in for, this would be equal to 1 over, I'm going to combine 2 natural log of 6 times 6 to the x plus 4 squared, and then because this is an indefinite integral, of course we need a plus c. So again, sometimes our problems look really intimidating, but as long as we try our u substitution, we're able to simplify and to solve. Okay, great job with lesson 68 with finding derivatives and integrals for bases other than e. Here are the 4 homework problems. So 1 and 2, you can see are finding your derivatives. So those are from examples 1 through 5. And then 3 and 4, you are finding your indefinite integrals. So you can use examples 6 through 9 to help you with those 2. As always, check your answers and ask your teacher if you have any questions.